Welcome back to Control System Lectures. In this video I'll introduce a control system design technique called the root locus method. Since this is an introduction, I'm just going to use this video to explain what the root locus method is and how to use the method to aid in control system design and analysis. Control system engineers are often confronted with problems of the following type. You have a system that's made up of multiple known parameters and one unknown or varying parameter, k. And since you don't know that one parameter, you can't know whether the system is stable or whether it meets your design criteria. Let me show you a quick example of what I mean so that it sinks in. If you have a system that can be described by this transfer function, you can see that there's one unknown parameter or one unknown coefficient called k. And you should be able to see that by changing that parameter, you're going to be changing the location of the poles of the system. Remember that the poles of a system are values of s that cause the transfer function to be divided by 0 or to blow up to infinity. And you can see from this polynomial that the value of k does in fact move the roots of this polynomial. So you have this transfer function, and now at this point you want to know the answer to one of two questions. The first is a question of control system design, and the second question would be the effect of variation on a control system that's already been designed. On the control system design side, the question is, what value of k should I choose to meet the required system performance? That is, having poles in the correct location in the S-plane. And on the system variation side, the question is, what is the effect of the variation of k on the poles of the system? That is, how sensitive is the system to a value of k that is slightly off what you have predicted? And trying to answer these questions is actually pretty simple. I mean, if you didn't know any better, you could just pick a random value of k, say k equals 0, and then plot the poles in the S-plane. Since this is a third-order system, you'd expect 3 roots of this polynomial, or 3 different poles for this system. And when k equals 0, those poles are here. Now you can pick a new value of k, we'll say k equals 1, and plot those poles on the exact same chart. And you can keep picking more values of k and repeating the process until you get to the value of k that you want, or you got to a sufficiently high value of k. And then connecting all of these points on the S-plane together is a drawing of how the poles move through the S-plane as you vary k. And this is exactly what the root locus method is doing. Now, I'll get back to the concept of design and variation of a system shortly, but first we need to take a step back, slow down a bit, and see how to interpret the locations of the poles of a system in the S-plane. The S-plane is drawn with real components, sigma, on the horizontal axis, and the imaginary components, omega, on the vertical axis. And each location in the S-plane corresponds to a particular waveform in the time domain through the equation e to the st. And through this equation, you can see that if s is a real value, this corresponds to exponential growth, or decay. If the real value is negative, then you're in the left half plane, and the system exponentially decays. And the further you are from the origin, or the further in the left half plane you are, the faster the signal decays. In the right half plane, the real component corresponds with exponential growth. And again, the further you are from the origin, the faster that growth becomes. The imaginary value corresponds to sinusoidal motion, or oscillations, in the time domain signal. These locations always come in pairs that are complex conjugates of each other. These pairs of complex conjugates are the results of dealing with real time. And the further the poles are from the real line, then the faster the oscillations, or higher frequency. And a combination of real and imaginary values are a mix of the two, both exponential and sinusoidal motion. Even though both poles and zeros of a system are needed to characterize the response to a forced input, only the poles of the system are needed to dictate an unforced response to a set of initial conditions. And this ties directly to the stability of a system. And that's why when we're talking about stability of a system, we're really only looking at the poles in the transfer function. So knowing the location of the poles in the S-plane not only help you determine stability of the system, but also whether response will be oscillatory and at what frequency, or exponential, and at what rate. But there's even more information hidden in this graph, a third set of lines that can be drawn on this chart as well. These are lines of constant damping ratio, and they radiate out from the origin at a value of cosine of phi. So two separate poles on these lines would have the exact same damping ratio. Let me give you a quick side note. Don't be confused between the term damping ratio and the term damping coefficient. They aren't equal. The damping coefficient is the value of the damping term, or Newton seconds per meter, so that when you multiply it by a velocity, you're going to get force out. This damping coefficient can have any number of values based on the size of the system that you're developing. The damping ratio, on the other hand, is a normalized unitless damping value, so that a 0 corresponds to no damping at all, which as expected puts the poles on the imaginary axis, and a 1 means perfectly damped, so that there's only exponential motion, which puts the pole on the real axis, and anything greater than 1 means overdamped. It's more like a damping percentage, not a damping total, and it's that damping ratio that can be seen easily in the S-plane. So you might be asking, why did I explain all of this information to you instead of talking about the root locus method like the video title says that I should? Well, because it's important in understanding the usefulness of the root locus method. Control engineers have to design control systems to a set of requirements. And a lot of the time, those requirements come in the form of damping ratio, exponential growth or decay, or natural frequency of the system. For example, one of the requirements could be that the damping ratio has to be greater than some value. If it's stated like that, that means that the poles of the system have to be inside this pink cone, or less than that damping ratio. If you're given a requirement about time to half, this means that the mode must decay to half its value within a certain amount of time. And since the further a pole is from the origin, the faster it decays, then in order to meet that requirement, all of the roots or the poles must be to the left of that particular time to half line. And finally, if you're given a natural frequency requirement, like the mode has to be slower than 1 radian per second, then the poles have to fall within this yellow band, or slower than 1 radian per second. And of course, more often than not, you're going to get some combination of these requirements. And so you could just build them up and determine where the poles of the system need to lie in the S-plane. So now that we understand how pole locations affect the system, let's get back to the root locus method and our design questions. Let's say that you want to design a mass spring damper system that meets certain requirements. And we'll say that the requirement is that the damping ratio for the system must be greater than or equal to 0.75. However, you don't have control over the entire design. The spring department is in charge of choosing a spring, and it gets to pick the spring constant, which they pick as 1. And the mass was developed by your marketing department, and they said that a mass of 1 would sell the best. So now you get to pick your own damper, and with any damping coefficient you need in order to meet the system requirements. So your transfer function for this system, from input u of t to output x of t, would look something like this. And notice that I left the unknown damping coefficient b as a variable in this transfer function. Now the root locus method gives us a way to plot how the poles of this system move in the S-plane as we take the unknown parameter b and sweep it from 0 to infinity. Now this lecture isn't going to focus on how to draw the root locus plot, just on how to interpret it and use it. Drawing a root locus by hand is useful, however most of the time you'll just use a software package like Matlab to draw the root locus for you. Now here's what the root locus would look like for this system. As you can see, the poles start here when b equals 0, which is undamped oscillations exactly as you would expect from 0 damping. And as we increase the damping, the poles move further into the left half plane until you get to the critical damping value, where the two poles split and separate on the real line. So now at this point I can draw my two lines of constant damping ratio at 0.75. And I know that I need to pick a value of b that puts the poles of this transfer function somewhere along that blue line. I'm going to choose a value at these yellow x's because this allows me to buy the smallest, lightest damper I can while still meeting system requirements. And so we need a damping coefficient of 1.5. I wrote zeta equals 1.5, but I really meant B equals 1.5. However, you're about to ship your spring mass dampers out to your customers all over the world when the spring department comes running to you in a panic and says that the spring constant changes when it's subjected to temperature variations. When the spring gets really hot, the coefficient drops to 90% of its normal value, and when they get cold, the coefficient's raised to 110%. So we need to know how sensitive is our design to this variation. And now we can use the root locus method to determine how sensitive the system is to changes in the spring constant. You can replace the spring constant with a variable k in the transfer function. Then either manually or with a software package, you can run the root locus with k varying from 90% to 110% of the ideal spring constant. And when you do that, you'll see the following graph in the S-plane. First, let me redraw our requirement, which is the lines of constant damping ratio. These yellow X's are our ideal spring constant at 1, and these red lines that I'm drawing is the root locus, where it goes from the hot value of 0.9 K to the cold value of 1.1 K. And you see that when the springs are hot, we still meet our requirement. However, when they're cold, the damping ratio goes down to 0.715, which doesn't meet our requirement. And now your team has a decision to make. Do you restrict the operating temperature on the low end so that the device still performs, or do you add a warning that performance will be degraded in low temperatures, or do you call back all of your parts and redesign it so that it works for all reasonable temperatures? Unfortunately, the root locus method can't help us with that. But watching how the roots move through the S-plane is powerful, and the root locus method helps us do that. And if you have access to a program like Matlab, then you can generate root locus plots easily and interpret the results quickly. However, when Walter Evans developed this method 60 years ago, there was no Matlab, and manually calculating the roots of a system for multiple values of k was time-consuming. So there are a set of rules that you can follow to manually draw the root locus. And like I said earlier, it's good to know how to do this because you can start to imagine how adding feedback or upping the gain in the system will move the poles without actually ever having to model anything. And ultimately, it'll help you become more familiar with your system and make you a better controls engineer. I'll cover the rules for drawing a root locus in another video. So that's all I have for right now. If you have any questions or comments on what I've stated, leave them below and I'll do my best to get back to you and answer them. Also, don't forget to subscribe so you don't miss any future videos, and I'm on Twitter at Brian B. Douglas. Thanks again for watching. See you next week.